Hi everyone, hope you are all safe at home and staying healthy in quarantine. We, the department and faculty members, are missing your charming faces. Hence, we decided to design the Z module to stay connected with you people. Welcome to the Z module, and the Z module is about the feedback in amplifiers. As we all know, we have discussed about the feedback and types of feedback and the expression for the voltage gain of amplifier with and without feedback in the last class. Now, today, this E module is going to help you to gain knowledge about the amplifiers which are used in public address systems, stereo amplifiers, buffer amplifiers. Can you guess what type of feedback is used in all the systems? Yes, you are right. It's negative feedback. And how this negative feedback is advantageous and why it is used in all these systems. So today's module is going to give you a brief information about the negative feedback. Now let's get into the module. To have a quick recap, we all know the definition of the feedback. So this is a simple feedback system where we have the voltage source Vs and the amplifier A with any active device. The active device may be BJT or UJT, and the amplifier will give a kind of output voltage which is V0, and from this V0 a part of the voltage shall be taken through the feedback network to the mixer where the input voltage and the feedback signal Vf will mix together. So we can define the feedback simply. What is feedback? It's defined as a process in which a part of the output signal is returned back to the input. And there are two types of feedback. One is positive feedback, the other is negative feedback. What is positive feedback? If this feedback signal which is taken from your output is positive, that is, if this Vf is in phase with Vs, then the feedback becomes regenerative. That is the positive feedback. If on the other hand, if this Vf is in out of phase with the Vs, then the feedback becomes degenerative feedback, that is negative feedback. So this is the simple circuit where the amplifier is used without any feedback. So this is an example for the open loop system, because the loop remains open. We do have got one input terminal and one output terminal. There is no any connection between the output and the input. So this is a simple amplifier without feedback, for which the gain of the amplifier can be calculated from the ratio of the output voltage to the input voltage. Now, if we introduce the feedback network beneath your active device, then the voltage gain becomes V0 by Vs. Whereas in the previous case, if it is without amplifier, it is V0 by Vi, that is input voltage. If it is with feedback, then AF is nothing but V0 by Vs. I hope you can understand the difference between the with and without feedback. Good. Now, let us focus our attention on negative feedback. What do you mean by negative feedback? As we discussed now, Vf is going to be in opposite phase with Vs, where you could see the wave patterns here. This is your original source voltage, which is fed into the amplifier through the mixer. So initially there is no any feedback voltage, only Vs will be fed into the amplifier. and there is an output voltage which is coming out of the amplifier where we could see some out of phase with V0 and Vs. Yes, we all know that this amplifier will always give 180-degree phase shift to the signal. So the V0 is 180-degree phase shift with Vs. Now this phase shifted signal is fed back to the feedback network and it reaches the mixer, and we all know that this feedback network will never give any phase shift, so it is only 0-degree phase shift. So whatever the signal we are feeding it from the output part to the input will appear across as Vf. So you could see the phase difference of Vs and Vf. So what happens here in case of negative feedback? Vs and Vf are in out of phase, point number 1. And point number 2, the feedback factor, that is this beta, is nothing but the ratio of Vf divided by V0. Vf divided by V0. And let us see how this negative feedback is advantageous. First thing, whatever be the amplifier, the gain is the prime parameter which is going to decide the performance of the amplifier. So this gain depends on two main parameters. One is it depends on the power supply voltage, and again the gain depends on the parameters of the active device. Now what is the ideal op-amp? What is the role of the ideal op-amp? The ideal op-amp should, in case of an ideal op-amp, the gain of the amplifier should be independent of the change in power supply voltage and the change in parameters of active device. Now let us check whether this negative feedback achieves the stability of gain in case of change in power supply voltage or in case of change in active device. So to start with, we know the expression for the voltage gain of the feedback amplifier. That is, if in case of the negative feedback, AF is A divided by 1 plus A beta. What is A? Internal gain of an amplifier. What is beta? It's in feedback ratio, that is, which is decided by the ratio of R1 and R2. Yes, good. Now, if this feedback factor is very much greater than 1, then what happens to this fraction? Denominator is too high. In that case, we can neglect the 1. So, just by cancelling A and A, we will be left out with AF as 1 by beta. So what we could conclude, AF is the gain of an amplifier with feedback is independent of A, but it depends on beta, because there is no any A term here, only beta is there. So what we could conclude, AF is independent of A, but it depends on beta. So the main and simple condition to achieve the stability is A beta greater than 1. So this is the condition for which the gain stability is achieved in negative feedback amplifiers. Now we shall check if there is a change in internal gain of the amplifier, that is, if A changes, what happens to AF? Whether the AF will change or the percentage change in AF will be high or low. So we shall analyze that. So to find the change in AF, we need to find the derivative of AF with respect to A. So it's a simple U by V formula where the denominator is V, the numerator is U. So what is U by V, derivative of U by V? Yes, you are right, V squared U dV plus V du. Differentiate U and V terms and you will be left out with 1 by 1 plus A beta the whole squared. And just by rearranging all the terms, and if you divide this DAF by AF on both sides, you will be left out with dA by 1 plus A beta A, where what is the term which is on the left hand side? Change in gain of the amplifier with feedback. What is this? Change in internal gain of the amplifier. See here, there is a term here in the denominator. What is this? A beta. This is very much greater than 1. So we can neglect this one. Again, this denominator is going to have a very high value, which makes this ratio too small, meaning that DAF by AF is too small. So what is DAF by AF? The change in voltage gain of the amplifier with feedback is always much lesser than the change in internal gain of the amplifier. So the gain stability is achieved in case of negative feedback amplifier. And the second advantage is how far the distortion and noise, whether the noise and distortion are reduced or it increased. So to have a glance over the circuit, again this is going to be your source voltage, an amplifier which is constructed with any active device, and if D is the distortion of the original signal and DF is the distortion of your feedback signal. So how to find out the distortion in the feedback signal? What happens here in the mixer? From the left, from the input voltage, the distortion is D. And what is this A beta DF? DF is given back to feedback, so it becomes beta DF, and here it is A times DF. So what is your feedback signal? Feedback signal is A beta DF. Okay, so just by rearranging the terms, you will be able to end up with the formula to calculate the distortion in feedback systems. So here too, we can have the same conclusion. There is a term of A beta in the denominator, which makes the ratio too small. When A beta is very much greater than 1, the denominator is too high, the ratio becomes too small. So the distortion in feedback system is always small. This is my second advantage. And while talking about this input impedance, here the same type of circuit can be considered where this VI and II are the parameters of the feedback amplifiers, and VI prime and II prime can be treated as the parameters of the amplifier without feedback. So we know the impedance. Impedance is nothing but the resistance. Resistance is voltage divided by current. In case of the feedback amplifier, VI and II are the parameters. So what is it? IF? Is impedance, I is input. So input impedance of the feedback amplifier is VI by II. And what is the net input impedance of the amplifier without feedback? Here the F should be removed here in this case. So Zi is equal to VI prime divided by II prime. So we know the net input voltage which is fed into the amplifier, that is VI prime is equal to VI minus beta V naught prime. What is V naught prime? A times VI prime. So all these things that we have discussed in the expression in the calculation of voltage gain expression. So we are just recalling these two expressions, and by substituting it we will be end up with input impedance in feedback system increases because the A beta term is in the numerator. When this value is very much greater than 1, obviously your ZIF will always be high. Now, what happens to the other important parameter called output impedance? So this is the circuit to be considered to calculate the output impedance, where we have replaced the voltage source A beta V naught, which is in series with the input resistance Z naught, which is going to be in series connection with V naught. Just by simply applying the Ohm's law formula, we can calculate the net voltage in the circuit. What is net voltage in the circuit? V naught plus A beta V naught should be equal to, that is V is equal to I times R. So V we have calculated. What is I? It is I naught, and is it instead of R we have substituted impedance here. So it is Z naught. Just by rearranging all the terms, we will be end up with V naught by I naught is equal to Z naught by 1 plus A beta. What is the left hand side term? Nothing but impedance, output impedance in feedback network. This is output impedance without feedback. Whereas here the situation is a bit different. Here the term appears in the denominator, which reduces the value of ZOF. Whereas in case of input impedance, it appears in the numerator, which helps to hold the high value of input impedance. But whereas here the A beta term is in the denominator, which reduces the value of output impedance. Now, what happens to bandwidth? We know that what is bandwidth? The difference between the lower cutoff frequency F1 and the higher cutoff frequency F2. Here in this case, lower cutoff frequency F1 is lowered by the factor 1 plus A beta, and upper cutoff frequency is raised by 1 plus A beta. So the bandwidth is nothing but difference between F2 and F1. Since F1 becomes too small, bandwidth is nothing but it's approximately equal to F2. So what happens here in this case? Here too bandwidth increases because of negative feedback. And there is another parameter called gain bandwidth product. This is the product of gain and bandwidth, which always remains same in case of negative feedback systems. So to conclude the merits and demerits of negative feedback, whereas in the merits column we do have got the gain stability, reduction in noise and distortion, high input impedance,